So, in the quest of looking for cheaper alternatives to attempting to make LED or LED or DEL lights less flickery under AC mains. So, I had a video of doing AC versus DC and the camera shutter roll of testing to see if there's any flicker on LED lights, Christmas lights, under certain situations and certain conditions. And we have proven that there is no AC or there is no DC flicker when you run your lights on direct current power. The next issue was making that so-called clean DC power in a couple of different methods, and one of them is you can build a converter to convert AC 120 volts or whatever's coming out of your wall into DC current. So you'd have to get a transformer, and the sweet spot for that is anywhere from about 80 to 90 volts, give or take. The problem is that if you want to run like a lot of lights, you're going to have a pretty hefty system, which means that it's going to cost quite a bit of money. And sometimes the parts are not available, and sometimes the parts are available, but it's a lot of money. So it's not really cost efficient to make such a contraption. I mean, if you're doing it on a small scale, you can run quite a bit of lights off a pre-built, which is about 300 milliamps. You can run, a small tree off of that, because I've done the numbers on what Christmas lights uses on AC and DC and all that other good stuff. So that's back in the December and early January 2023, 2024 videos that I had on. It all started with the madness of True Tone bulbs and stuff like that. So on the quest looking for a different answer, I just happened to stumble on a simple circuit, and we're going to build it today to see if it does work, or at least maybe cut the flicker down by a lot. And the only way to really tell if it's working is setting the shutter speed on the camera when it's on off of this wacky circuit I'm going to make, to see if it works. So we need a couple of bits, and some of these parts you might have on hand, and some you might have to buy. So I had to buy at least two parts. So first thing we need is a way to connect power. So we need an outlet power, and we're going to need an inlet power. So this is from old Christmas lights. So we got a non-polarized plug here, and this is a 3-wire. So if you don't know about 3-wire plugs, it's nothing to be intimidated by. 2 wires are going to be common. So one side's going to be hot, one side's going to be neutral. So being that this is non-polarized, we kind of want it to be polarized, because it's going to be important later on when you build this thing and you hook lights into it to see, because some lights may work and some lights may not work off of this system. So we're going to use a non-polarized plug, because I'm just using parts and scrap on hand to build this thing. So we need an input. So based on what I just said, we're going to make this a polarized plug, as in this plug, we're going to make it so the wires face down. So what that means is that the right-hand plug or prong is going to be the hot side of the plug, and the other side is going to be neutral. And my reasoning for this is that when a plug is like this, water can get in the plug and go right into the housing of the plug, where When it's the other way, all the rain sheds away, or wetness sheds away from the plug. But this is experimental, doesn't really matter. But if this does work and you decide to build one, you definitely want to have polarized plugs, and you're going to have, when you're done, you're going to be putting this into either an outlet box or a project box or something. So we got an input, we got an output, and of course on our output it just happens to be polarized. So we're going to be making sure our small blade is the hot side and stuff like that. We might need a little bit of wire here. We're going to be needing a 4 watt up to a 25 watt regular candelabra base lamp. The wattage comes in later. It's very interesting how this bulb's going to affect the circuit. And of course, a couple of other bits. Of course, if you're an electronics guy, you're going to have some diodes floating around. So in the hoard, we're going to be wanting a 400 volt 1 amp or an IN4004 diode. So we need one of them. You can go either way on this. You can either use some kind of candelabra-based lamp holder or an old Christmas C7 or something like that. But we need a lamp holder for our lamp, because we're going to be hooking this in an untraditional way. We're going to be hooking it inline. So whatever, it's only going to be hooked on one wire. So our little input wire here is going to be connected here, and then our remaining input wire to our diode is going to be, so it's going to be in line. So current is going to be going in this lamp holder up through the filament, back down out of the filament, and coming back out. So it's not being, like I said, in line. It's not being hot and neutral. That's not how this is being hooked up. We're hooking this up in line. So that's going to be part. And then the other thing that most people are not going to have, even the biggest 99% of the electronics buffs, you're going to be needing a big honking capacitor. So you're going to be needing a 200 volt 100 microfarad capacitor. And the only way you're going to find a capacitor, even if you're scrap hoard, is if you're dealing with like vacuum tube type equipment. So not a very common capacitor that you might have or may not have in the hoard, depending on what kind of a hoard you got. So I don't have that kind. Even the biggest capacitors I have is 63 volt. That's the biggest I got. So needing one of them. And of course, you might need a little bit of wire. We're going to be doing temporary connections here. So we're going to be using Wagos and stuff like that. So let's build this wacky thing. So first thing we need to connect our plug here to our lamp holder here. So we'll just, and of course this is all temporary. If this works, it'll be wonderful. If it don't work, well, it doesn't really matter, because for me, it's no real loss. So we'll hook that on like that, and it's just going to be very temporary, so it's going to be a little sketchy. And of course, like in the last couple of videos with me playing with 120 volts AC and 120 volts DC, you want to be careful playing around with voltages like that. Of course, AC will give you quite a shock, but DC is a little bit more deadly, especially 120 volts DC. It's a little bit more unforgiving, where if it goes across your heart, it might stop it. So you definitely want to be careful, and don't be screwing around, and pay attention to what you're doing. So we got our little diode here. And of course diodes, they only shunt electricity one way. It's because it's a one-way valve. That being said, our little band, which is on my right side here, is going to be going to our plug here, our hot side of our plug. So we'll hook that up. So that takes care of that. And now we're going to be connecting our output. So on our plug here, we're going to be following the, because it is polarized, so one of our wires is going to be the hot side and the other side is going to be the neutral side. So we're going to be hooking that up. And we're also going to be hooking up our capacitor. So we got a negative side and we got a positive side. So the longer leg is always the positive. That's going to be going to our hot line. So we're going to connect this and our diode together in our little Lego and hope that it sticks on there. So that looks secure enough. So now we're going to take our other leg here, and now we need to make a jumper here for our neutrals. So we'll make a wire connection here. And this wire is older than hell. And it's all the crappy stuff because it's already turning black. So we'll finagle our wire here so we can get both the wire and our capacitor hooked in together. Ain't got enough. Need more. That baby goes in there deep. Okay, that's secure. That's secure. So everything's secure there. So now we need to make a little jumper. I'm going to go from point A to point B. We'll get another Wago. Stick him in there. Lock him down. Stick the other side in. So that is the circuit, and I'll put a little diagram up so you can follow along, or call it a complete failure. So now, to complete the circuit, we just stick our little bulb in here. And now the circuit is done and we're ready to plug it in and test it out. So I got to get a set of LED Christmas strands, and then we'll test this this wacky circuit out to see if it works. So that'll be coming up next. So I got a strand of LED Christmas lights that we're going to plug into our little contraption here, and hope that it don't blow up. So we're going to plug in our connection here. And when I first plugged it in, the light did glow because it charged up the capacitor. So right now we have a live voltage here, so we definitely want to be careful what we're sticking our fingers around. So we'll do a little voltage test here to see what we're getting. So luckily with these little guys, they got a little test connection that we can test. The probes are too big. So we'll just stick it in the outlet, just like any other maniac. So it's not registering any AC volts. So now we'll hook it up to DC voltage. So that's 163 volts. So you're going to be saying, well, that's a lot more than 120 volts, and you're right. But that's unloaded. So now we're going to plug it in and see if they work. So right now we are plugged in, and our little nightlight bulb, our 5-watt lightning bulb, is glowing. So I think you can see it. I put my hand around it. See it glowing? So the circuit does work. So now that we are loaded, the circuit is loaded, we have a DC voltage of 92.2 volt. So now we got a voltage of 92 volts DC. 92 volts DC. Well, you're going to say, well, that's a little under voltage. Well, you're right. It is. But our lights are pretty bright, in my opinion. They look pretty bright. The question is, do they flicker? Let's find out. So let's bring a strand over, or part of a strand over. Of course, I can bring you in closer. Hope I don't knock anything over. We're gonna get the lights right next to the camera here, so we can see if there's any flicker. And then we're going to start screwing with the shutter speed. So here we go. So I started getting flicker with true tones about 170 on the shutter speed. So that's on the true tones. So now we're going to start creeping it up. I don't see any flicker. None at all. That is cool. I like that. I can't believe it worked. Amazing. So, how does the circuit work? You're going to be asking. Well, it's very simple. Power's coming in at 120 volts AC. It's going through our nightlight bulb. Our nightlight bulb is acting as a big resistor. Since it's, it's tungsten, it's got a certain amount of resistance and stuff like that. And being that it's drawing current, our little bulb is glowing a little bit. So goes through our hot side of the bulb, or it's in line with the lamp. It's going through our diode. Our diode's only allowing the AC voltage in one direction. Of course, we know that AC voltage, it's always going back and forth. Or on an oscilloscope, it's going in a wave. So it's got an on cycle and an off cycle. So when it's off cycle, the power's trying to go back the other way, where it can't. The diode was blocking it. So being that the AC power going through the circuit is on and off, on and off, on and off, on and off, right? Our capacitor is making up the difference for the off state. So that continues the power of the system. And of course, it goes through the lights, comes back through our neutral, and that's how it works. So a very simple circuit, and it does work. To convert AC power makes it to DC power, even though it's 90 volts. But we can change that if we change the bulb, if we can find a different kind of a bulb. So I just happen to have a 9 watt. This is a 9 watt bulb, and we can change that to see what it does. So we'll unplug it. Now the only downside of this circuit is that the lights are going to keep going on until the capacitor is empty. So that's the only drawback of this little circuit, is that the lights will continue to glow until that capacitor is discharged. Now remember, we got about 90 volts DC on there, 92 volts DC, so you want to be careful. So that's that. So we'll unscrew our bulb here, and we'll put a 9 watt bulb in here. Now you can put all the way up to a 25 watt bulb, depending on what you want to do. And then we'll plug this back in. So here's our 9 watt bulb. Now it's brighter. I can already tell it's brighter. And our little bulb is glowing, as you can see. What's our voltage? We'll test our voltage right now.
Is about to enter stand AC voltage. Capacitor diode temperature auto mode. Already on auto mode. DC voltage.
Now we're up to 106.
DC 106 point.
So we went from what, 92? Or 90 some odd volts to 102. So I bet if I were to go up in wattage of bulb, we can tailor this to have the desired of brightness that you want. So they're pretty bright. I would say they're about equal to if they were plugged in AC mains. Now one thing you want to keep a note is, and this is why you want to do a voltage check, you don't want to be driving these. I wouldn't drive these any higher than 115 volts, 120 volts, because you might be overdriving the LEDs. So I would personally keep it about 9 watts, 9 to 10 watts. Now you can play with it all you want. I mean, you put the full 25 watt incandescent bulb in here and have these things, supernova in brightness levels. But I think this is pretty cool. And this is dirt cheap. I mean, to get a couple of parts, get a lamp holder, a project box or an outlet box or stuff like that. You can even rig this up to be like a traditional outlet, a wall outlet. But of course, you want to dedicate it to just for Christmas stuff. So that is flipping cool. So I'll put that diagram up there. So for a couple of dollars in parts and something that you might even have laying around, even outlets, even an extension cord, or you got to have some kind of plug laying around. But if you got to buy a plug or make your own outlet up, it's going to be a hell of a lot cheaper to do this circuit than it is to buy a transformer and build it that way. Now, the only limitation of the circuit is going to be the limitation of the diode. So it's a 1 amp diode. So you don't want to be overdriving the diode. You burn it up, and then you'll be replacing parts and stuff like that. So I would assume that the limitation of the system is the diode. So this is not going to draw a lot of power. I mean, just as it is, we can test the amperage, milliamp amperage draw on this system. So that's not a big deal. And I would assume that you can run quite a few sets on this thing, on this simple circuit, as long as you keep it within that 1 amp range. I would imagine. So this is a set. This is a set of I don't know, 70 or something like that. So we can hook this in line and see what it does. So this is exciting. This is interesting. This is a dirt cheap way to take all of it. Take 100% of the flicker out of your AC mains, LED lights. So now you can have LED lights because the True Tones, that's a very nice light to have, and because they the way they designed their bulbs, they got very nice color rendering. Because I can understand some people, they don't like the looks of LEDs because it's too cold or it's too stark or too in your face and stuff like that. And I agree. I do agree with that. But it's all your preference. If you don't like that really starky, like the white on these sets, they're really starky white. In the red, the red is a nice red, but there's certain colors like the greens and the blues. Some people are not turned on by that. They're like it's a very harsh, nasty looking color, but the other colors are very nice. So we'll turn our meter on here and see what we're drawing for DC current. And of course, we're only drawing for this particular set 18 milliamps. So we got a long way to go to get up to 1,000 milliamps to meet that bulb. I mean, not bulb, but diode maximum capacity. Would I run a full amp out of here? Probably not. But since this thing is so dirt cheap to build, you can build several of these and run your whole system off of it. Very cool. It's a very simple circuit. I had to do a lot of digging to find it, a simple circuit like this. And there's a couple of different variations of this, but I think this is the most robust and easiest to play with. So to go over a review, we got AC coming in. We're going through a candelabra-based light system here. So you can either rig up a regular socket, or you can have one of these little fancy socket holders. And we're using our 4 all the way up to 25 watt nightlight bulb to act as a resistor for the system, because we got to tone down the power a little bit coming in. Then we're going through a diode. The diode is only allows electricity to flow in one direction. We are dealing with AC mains, so it does go on and off, or in and out, or up and down. Our capacitor is making up the difference for the off state or the downside of the AC wave, and then it goes through our lights and back out through our neutral. Our nightlight bulb is kind of like our dimmer control. Now you're going to say, well, how come you don't put like a rheostat on there and stuff like that? Well, unfortunately, rheostats are very tiny. They're just not built. If you were to have a rheostat for this circuit to run the maximum amount that the the circuit can handle. The flipping thing would be huge. Should be like a 20-pound wire around rheostat to make this work. That's why the nightlight bulbs. Nightlight bulbs are resistive. They have a known resistive value in it, and you can get a plethora of bulbs for this. And of course, the only way to really check the wattage of a bulb is to put it on a watt meter, see how many watts it really is. Then you can fully tailor your lights to operate at a different brightness level. So these are pretty bright for a 9 watt. So we'll go back to our little lower wattage bulb here, and it'll be a lot dimmer because it was only running at 90 volts. So I can tell by eye. You guys on camera probably can't tell, but numbers don't lie. I did the voltage checks on between the 5-watt bulb and the 9-watt bulb or 10-watt bulb, whatever you want to call these things. And they're all going to be different wattages because you can get a pack of 4 of these things and they'll all be different. So these are running about, a little over 100 volts. So very nice. Of course, the lower voltage, the longer they're going to last, people. We all know about LEDs and your traditional overhead lights and stuff like that, and they burn out quickly because they're being overdriven. These things, of course, you're going to have bad blunders, bad manufacturers and stuff like that, but LEDs, they should have a very long life. They should have a life where they, on a consistent basis, after whatever amount of hours, 50,000 hours, they should start dimming. They should dim to almost 0 and then go out. Does that happen? Yes, it does. I've had an acrylic sign up here that was on many hours, 14, 16 hours a day. I had it running for I don't know how many years, 9, 10 years. The lights over time dimmed to the point where it was time to fix it. And when I did fix it, there was not one LED out. They all dimmed like they should have. When I did the info globe LED repairs, something that has been hanging around the planet for 20 years and probably in service for that same amount of time, the LEDs did their job. They remain lit, but they dimmed. That's what they're supposed to do. That's how they're supposed to die. So I hope this video answered a lot of questions. It certainly did for me. There's got to be some way, shape, or form to build something for dirt cheap and something that wouldn't be too invasive to build. Have little boxes. I mean, do I have any boxes here? No, I don't. But you can stick, I do have a little box. You could stick this simple circuit in a little box like this. And just have a wire going in, a wire coming out. You can even put the nightlight bulb in because this ain't hot. I mean, it's still room temperature. So you could stick that right in the box with it. Of course, if the lights go out, you got to check your bulb. So very cool experiment. It was 100% success. I hope you learned something. I hope the ones that are diehards, I hope they watch this video and I hope they build this circuit and make a video on it. Of course, they'll have to give me the credits because I made awesomeness and we tested it and we debunked it and all the other good stuff. So a very simple circuit, very easy to disguise it. I mean, stuff like this, you could, like I said, you could put it in a little project box and make it disappear. And, of course, there is going to be a day where you're not going to be able to buy traditional incandescent Christmas lights. I mean, yeah, a lot of people are buying them up because they need spares. They need the bulbs, really. And the problem with the bulbs is that the bulbs, they know they got you by the balls, so they're jacking the prices up on there. But it's cheaper to buy sets of lights and steal the bulbs out of them than it is to buy the replacements. But there are certain places where you can buy stuff in bulk. It's still not too expensive to play, like the mini lights. I mean, yeah, depending on where you buy them, you could get, bent over a coffee table and stuff like that. But if you buy it, if they have it, if they are available, buy them. But stuff like C7s and C9 bulbs, yeah, the incandescents, eventually you're going to dry up. It may be 10, it may be 20 years, it may be 25 years before, they're just not, these companies are just saying in China, well, there's no money in it anymore because, nobody's buying them, everybody's buying LEDs, and they just stopped making them, and that's just going to be the reality. So, enough of me rambling. I hope other people watch this video and make this circuit, because I know some people are sensitive to the flicker. We did test the flicker. There's no flicker because it's DC power, and it's clean DC power. So that's it for this video. Thanks for watching, and we'll see you on the next one. Bye-bye.